Good afternoon and welcome. Today we're turning to the fourth major theory of technology safety and accidents, which are valuable in the context of the topics of this course. This is the engineering-oriented theory of system safety, which has been constructed by Professor Nancy Leveson and many other researchers. Nancy Leveson is a senior professor of aeronautics and astronautics at MIT, as well as a professor of engineering systems. And she has done path-breaking research on system safety and software safety for several decades. She's the author of a book which I especially admire called Safeware, System Safety and Computers. And she also played a critical role in the investigation of the Challenger disaster. She, as I recall, chaired the subcommittee which reviewed the software systems which were in use in the Challenger. Her work and the couple of essays which you're reading, I decided not to ask you to read her most recent book, but rather several of these essays. These are just outstanding presentations of the orientation which she brings to the analysis of engineering safety and system safety and technology safety. She is an expert observer, and in the case studies which we are examining, we get a really insightful analysis both of the technical characteristics of those systems, but also of the forms of organizational behavior which are implicated in a number of accidents. And in fact, she finds a number of common features across the accidents which she considers. Of the essays that you've read for today, the one which I find the most useful is her study of accidents in the space in the space program over a number of years. She writes a very interesting kind of orienting view about what we need to do in order to have the beginnings of an understanding of safety and accidents. She writes these words: "The first and most important step in solving any problem is understanding the problem well enough to create effective solutions. To this end, several software-related spacecraft accidents were studied to determine common systemic factors. Although the details of each accident were different, very similar factors related to flaws in the safety culture, the management and organization, and technical deficiencies were identified. These factors included complacency and discounting of software risk, diffusion of responsibility and authority, limited communications channels and poor information flow, inadequate system and software engineering, inadequate review activities, ineffective system safety engineering, flawed test and simulation environments, and inadequate human factors engineering." This is her summary conclusion in the study of these half dozen space program accidents. She also writes what I would describe as almost an engineering credo about the origins and the appropriate analysis of accidents. So again, quoting from Leveson, this time in the Leveson-Daouk essay: "In complex systems, all dynamics, despite their complexity, arise from two kinds of feedback loops: positive reinforcing and negative balancing. In system dynamics terms, degradation over time of the safety control system, as represented by reinforcing loops, would lead inevitably to an accident. But there are balancing loops, such as regulation and oversight, that control those changes. In Ontario, one of the cases she considers, such feedback and monitoring controls were reduced. The mental model of the central government leaders and the ministries responsible for water quality about the current state of the water system became increasingly divorced from reality. A belief that the water quality controls were in better shape than they actually were led to disregarding warnings and continued reduction in what were regarded as unnecessary regulation and red tape." Interesting to read that paragraph and consider the Flint water crisis. So what is a system accident? This is her central point, that the most important and the most worrisome accidents within modern technology are what she refers to as system accidents. So what is a system accident? Quoting here, system accidents are caused by interactive complexity and tight coupling. Parenthetically, very similar to the analysis offered by Charles Perrault. Software allows us to build systems with a level of complexity and coupling that is beyond our ability to control. In fact, we are building systems where the interactions among the components cannot all be planned, understood, anticipated, or guarded against. This change is not solely the result of using digital components, but it is made possible because of the flexibility of software. Note that the use of redundancy only makes the problem worse. Again, a point that Perrault makes as well. The added complexity introduced by redundancy has resulted in accidents that otherwise might not have occurred. So let's begin with technical deficiencies, and then we'll talk also about the organizational and management deficiencies, which she identifies. A key problem, which she identifies in multiple space program accidents, is what she refers to as inadequate systems engineering. Her basic view is that systems engineering is designed and intended to pay attention to components and their interactions. So systems consist of multiple components which are linked together in complex forms of interconnection, causal interconnection among them. And these interconnections are the sources of potential accidents because of unpredictable or out of control causal interactions. So what is the design process for a technology system? Well, ideally, we would like to imagine that we take a group of very smart engineers who have been organized in a very logical way to engage in a design process with logical relationships among the modules. So they are organized according to what the objectives of the technology system are that they're designing. And then very logically, they develop a kind of a flow chart, an organizational diagram of the components and how they are controlled and how they work together to bring about the results desired, whether it's travel to Mars or normal operations of a nuclear power plant or whatever. That's the ideal case, where there's an organized, kind of top-down, rational process of design. What she finds, by contrast, in many instances, is that complex technologies are often designed incrementally, where the outputs of prior design are taken as fixed and satisfactory, and then the next stage of the development of the technology is layered on top of the older technology. In other words, systems are developed and modified and extended in ways which don't often involve a full look at the whole integrated system, but only at the new parts, and often the new parts are themselves not sufficiently critically analyzed. She also identifies what she calls poor or missing specifications. So what is the function of a certain module or a certain software module? The specification needs to be provided very specifically, and she finds in her analysis of the space accidents that often that is a source of mission failure. She also finds that in the cases that she considers, there's an unnecessary level of complexity and software functionality in the software control processes, which are implemented in space, kind of the space program. She finds that there are often violations of safety engineering practices in software design. There is inadequate review and testing in terms of the products of whether it's air traffic control system or modifications of air traffic control system or the control system for spacecraft. And in fact, early in the summer, there were the launches which occurred, I think it was the Boeing spacecraft, where errors in programming had led to premature firing of one set of booster rockets. And so it led to, in the end, it was not a fatal accident for the mission, but it was a dangerous action. And she also highlights what she calls inadequate identification of mission-critical elements throughout the mission. This is an important part of systems analysis, the need for intelligent engineering teams to walk through the expected performance of the system under design and then identify those places where a mistake or an incorrect signal or a failure of a component can lead to mission-critical failure. She accepts the point which we have been emphasizing throughout the rest of the course, that social and organizational causes are important components of major accidents and failures. And she gives a number of good examples in the space program. Quoting from her again, large-scale engineering systems are more than just a collection of technological artifacts. They are a reflection of the structure, management, procedures, and culture of the engineering organization in which they were created. That's food for thought. The causes of accidents are frequently, if not always, rooted in the organizations, its culture, management, and structure. And what kind of organizational failures does she highlight? Well, she talks about the diffusion of responsibility and authority, the idea that many functions of a complex process have been allocated to different teams, and then there is not a very good or specific oversight process to make sure that the activities and the decisions being made by the various teams are being properly communicated across teams and are properly implementing the priorities of the project. So limited communications channels and poor information flow are themselves a major cause of design error in the cases that she considers. Quoting her, all the accidents involved one engineering group not getting the information they needed from another engineering group. She also finds something which we've seen in other instances as well, that there were inadequate processes for reporting problems, reporting possible errors, possible points of failure, possible ways in which the designs which are being put forward may actually embody the possibility of catastrophic failure. The process needs to be one in which it is possible for engineers and software experts to bring forward their concerns about the process, but if that's not implemented appropriately, if engineers and people working kind of in the middle of these operations are afraid for their jobs or for their promotion or for their merit increases to report problems, then the organization cannot improve the product by attempting to address these problems. So what is Leveson's approach to system safety? That is, after all, her central contribution. Her primary focus is on the ways that engineers and design teams and managers can improve the design of complex technology systems so as to minimize the likelihood of accidents. In a sense, we could look at this as being a response to Perot, because what she is saying is that a nuclear plant or a chemical plant or an aircraft with good design engineering, with good systems engineering, with good oversight and testing and scenario evaluation, all of those complex technological systems can be made more safe. In a sense, it's almost like another pathway towards greater safety, an alternative to, or maybe a complement to, the idea of high reliability organizations. What Leveson is highlighting here is that the engineering itself can be improved, whereas high reliability organizations theory suggests that the organizational characteristics through which a technology system is created and managed and directed, those organizational characteristics can be improved. But in each case, the idea is incremental improvement through a different way of thinking about the problem of managing and designing a complex technology system. She also emphasizes something which recurs throughout her work, and that is the importance of thinking differently about accidents. there is a tendency when the FAA goes out to an aircraft accident, a tendency to look for a single point of failure and to design or to construct an accident tree which showed how this accident or this plane crash occurred. She suggests instead that to study an accident in any moderately complex technological system, it's necessary to look at the system, not simply the chain of causes which led to the outcome. In other words, not a causal tree or a causal chain, but rather the extended network of interconnections and influences which led to or contributed to the accident. Safety culture is also important to Nancy Leveson, and she means something a little different in her use of safety culture than do the theorists of high reliability organization, or at least I understand her ideas as being somewhat different. She emphasizes that there are a number of ideas about safety culture in industry, the emphasis on safety culture, which actually do not enhance safety. So highlighting workplace accident records as the measure of safety, this is not a helpful way of defining safety, and therefore we wouldn't expect it to lead to greater safety of the complex technology system simply because it doesn't focus on the right level of analysis. It doesn't focus on the system interconnections of the complex technology system. Instead, it looks at a relatively low-level question of worker behavior, basically. So her view is that, yes, safety culture is hugely important, but it's a culture which the focus needs to be on focusing on the real priorities of the organization and making it clear that maintaining exceptionless, safe performance is the highest priority of the organization. It's not that business priorities don't count or that political constraints don't count, but that a safe organization and an organization which designs for safety is one which places safety at the top of the list of priorities. And if it turns out that production goals or profitability or cost reduction serve as the driving priorities of the organization, then accidents are much more likely to occur. And ironically, of course, production goals and economic goals and profitability goals all suffer as a consequence. But her basic point is that an organization which focuses on safety will make the investments necessary to enhance safety, to avoid catastrophic error, even though those investments may seem wasteful from one point of view. From another point of view, they're exactly what's necessary in order to make the nuclear plant or the nuclear submarine or the gas plant safe over extended operations. A nice quote from the spacecraft article: while management may express their concern for safety and mission risks, that is, they may put out statements, we care about safety here at Corporation XYZ, true priorities are shown during resource allocation. Although budget decisions are always difficult when resources are constrained, the first things to be cut are often system safety, system engineering, mission assurance, and operations, which are assigned a low priority and are assumed to be the least critical parts of the project. And very interesting, in the Boeing 737 case, this is precisely what happened in the engineering process. The business concerns of the corporation led to a withdrawal of resources in the engineering and system engineering design of the software upgrades which were needed by the aircraft. Returning to a quote from her, budget pressures added to the performance pressures in the shuttle program. Budget cuts occurred during the life of the shuttle, for example, amounting to a 40% reduction in purchasing power over the decade before the Columbia loss. And again, her point is that budget pressure and then the need to control costs often leads to a withdrawal of funds or the inavailability of funds to take the steps which a thorough system engineering approach would require. So again, there's the in the work that Nancy Leveson does, she has kind of programmatic statements about safety, but probably the most kind of actionable and practical and important part of her work is formal. And part of this has to do with her treatment of accident analysis. So what is an accident model? She makes the case that an accident model is the way that we conceptualize what happens in an accident. And it's her view that the accident model we have in mind really affects very much what we find in the details of the accident. She argues that the accident model makes a great difference in the way that we look at a given accident. Quoting her, the most common system safety accident models have their roots in industrial safety and view accidents as resulting from a chain or sequence of events. Such models work well for losses caused by failures of physical components and for relatively simple systems. So that simple chain of events model of accidents works well in some instances, basically the 19th century, early 20th century factory, but she believes it does not work well in the complex systems of the contemporary world. That simple accident chain model is no longer adequate. We need a framework for understanding accidents from a systems perspective. We need to treat the software that is involved in controlling this complex activity, treat it as a system. We need to take into account the complexity, the tight coupling, the interactions between management and technology. We need to have a framework for analyzing failure, which takes into account all of these kinds of coupling and complex interactions. Parenthetically, I've referred numerous times to Andrew Hopkins. We've read and viewed some of his work. Relevant in this context, though, is his treatment of what he calls a safety case analysis. And it's his idea that, and it's not just his idea, but he gives a good explication of the idea, his notion that one way of increasing safety in complex processes, complex industries, complex technologies is to require that management and ownership should conduct a deep, detailed safety case analysis, which they are then held accountable for. They need to, I'll read what he says about safety case and then say what responsibilities that creates. A safety case regime, quoting from Hopkins, a safety case regime requires companies to adopt a systematic hazard management framework. This means that they must identify all major hazards and develop plans for how these hazards will be managed. In particular, they must identify the controls that will be put in place to deal with the identified hazards and the measures that will be taken to ensure that controls continue to function as intended. And the crucial part here is that Hopkins argues that the safety case analysis would then be used as a tool of accountability. Management and ownership of a process, the owners of a process, are responsible in two ways. One, they're responsible for the adequacy of their safety case analysis. Did they do a responsible and thorough job of analyzing what the hazards are? Secondly, did they have an adequate response to those major hazards? And then thirdly, did they act accordingly? Did they make the budget arrangements necessary to create the safety equipment, to hire the possibly redundant staff in order to ensure that the responses to the hazards identified in the safety case analysis, to ensure that those responses are in fact carried out? That is a very interesting approach because it kind of combines industrial safety with the idea that we need to look at a complex activity as a whole system, and I believe that Hopkins would agree with that as well. So coming back now to Leveson, she highlights what she calls a STAMP accident model, and this is an acronym: Systems, Theoretic, Accident, Modeling, and Processes, or STAMP. And you can, if you're interested, she's written extensively and her collaborators have written extensively. But here's the premise of the STAMP accident model. quote, accidents arise from interactions among system components and usually do not specify single causal variables or factors. In other words, look to the system, not to the chain of proximate causes. In order to pursue a STAMP approach, it's necessary to examine the design process, the control process which oversees the design, the control processes that oversee operations, and so forth. In other words, look at the ensemble of components, the ways in which the components themselves were designed, the ways in which their interconnections were designed, and the control systems, the testing, the evaluation systems through which those interconnections are evaluated. Quoting, systems are viewed in this approach as interrelated components that are kept in a state of dynamic equilibrium by feedback loops of information and control. This is crucial to her point of view, that we can understand the engineering problem of a power plant or a nuclear submarine in terms of processes which have been designed to do things like heat water and generate electricity, and then control systems which bring data from valves, from temperature measurements and so forth back for assessment. And if those readings, those measurements exceed or fall short of expected parameters, then control activities are invoked. So she has a cybernetic understanding of how a system works with normal processes, feedback of information back to a central or possibly distributed controller, and then control operations which adjust the processes according to what has been learned. So what are the components of a STAMP analysis of a given accident? Well, first of all, we need to have an account of what the constraints or the objectives and limits on bad outcomes are of the activity, the aircraft, let's say, the Boeing 737 MAX. And then we need to see, was there adequate or inadequate enforcement of the constraints? Was there adequate or inadequate execution of control action? And in fact, the 737 MAX is entirely relevant here because the misfunctioning of the navigational system, the air alignment or air attitude adjustment system, was specifically not controlling appropriately. So now moving on to another point, inadequate or missing feedback. The upshot of this view of STAMP analysis is what are the constraints, how are they implemented, and are they working correctly? This approach looks at a technology system, whether it's a water plant or a chemical plant or a rail network, as a set of processes and activities linked by the causal interactions which they have, with control functions and information feedback mechanisms to ensure designed functioning. And notice this is a thoroughly engineering-oriented approach to safe and proper operations of a system. Here's a diagram that I thought it was worth reproducing, but really what it represents is simply the complexity of even relatively simple processes. This is the water purification example that she discusses, and the feedback mechanisms, testing mechanisms involving the water purification plants and the Department of Health and the provincial government. These are very complex interconnections of feedback and control, and it's her view that this is kind of a minimal level of complexity compared to a nuclear power plant. So the system safety process involves a theory of systems engineering. We can't have safe power plants, or we can't have safe aircraft software if we haven't looked at the problem to be solved as a systems problem. We're designing a set of components, we're designing a system of components which need to work correctly both in normal circumstances and also in abnormal but occasional and possible circumstances, the negative or the accident scenarios. In order to have a good design process, we need to establish objectives and constraints, need to design the system to achieve the objectives and maintain the constraints, and then we need to implement controls on the active processes and measurements. We need to provide for information flow which is permitting feedback concerning the activity, and we then need to have the control function which says if the water or the steam pressure has exceeded a certain value, then open valve X and reduce the value. If we were to imagine, this is the final slide, if we were to imagine Leveson applying the system safety approach to the Boeing 737 MAX crashes, I think it would be very interesting. It's very possible, actually, that she has done this. She is an aeronautical engineer, and if anyone, including the team working on this, can find an analysis, that would be really very interesting. But if we were to imagine her providing it just on the basis of what we've discussed today, she might have these observations. This would not be the full analysis, as you've seen. Her approach is to go into a lot of detail, but the summary might be, first of all, the engineering process was badly flawed. It was not a systems engineering process. It involved inadequate testing and scenario construction. So that's the first point. It was a flawed design process. Secondly, the flight system needs to be understood as being larger than simply the navigational or the attitude control software system. That is a system, to be sure, but it's a system that fits into a much larger system, which includes the pilots, air traffic controllers, training systems, and so forth. And her view is, in order to understand the accident, it's necessary to understand the larger system, including the pilots, including the other people not in the flight deck. Thirdly, the design process at Boeing failed to give adequate consideration to the pilots, their training, their readiness for the flight conditions the software would subject them to. It is noteworthy that Boeing did not provide additional training on the use of this new attitude control system, and they did not require pilots to go through a new process of simulation-based training. They were basically informing pilots, this system is essentially the same as the one you've used previously, no special training required, but here is the handbook. We could also imagine that Leveson would find that the management of Boeing and the corporate direction of Boeing failed in its priority of ensuring air safety. It failed to provide the resources and the safety culture which was needed in order to do a proper system-level design of the flight system of this aircraft. And that failure to the public and to the passengers of the aircraft, including the several hundred, 400 people who lost their lives in these crashes, that failure is a hugely significant and terrible fault in the process. And finally, we could talk about the failure of the FAA, the regulatory failure, the failure for the FAA to mandate an appropriate system-level design process and an appropriate deep testing and evaluation process. So, thank you. Went on a little bit longer than usual, but it will be great to talk about these things on Monday.